Okay, so I'm going to start 10.2. Yeah. So in this section, we're actually going to solve differential equations using Laplace transforms. So the first thing we need to learn is how to do the Laplace transform of a derivative. Um, so if f has exponential order, which this is something that came up before, most of the functions, or really all of the functions that we're going to talk about in this context, have exponential order. When I say it has exponential order, I just mean it's at most exponential in the sense that this function is less than or equal to some constant times e to the ct, where c is some other constant. If that's the case, then the Laplace transform of the derivative is this. It's s times the Laplace transform of the original function minus f of 0. In other words, if I call capital F, because this is kind of standard, is to use a lowercase letter for the original function and a capital letter for its Laplace transform. If I call capital F the Laplace transform, I can write it this way. So why is this? I'll give you a short justification. It's basically because of integration by parts. What happens when I plug in the derivative to do the Laplace transform of it? This is the formula for a Laplace transform, meaning that what I would want to do is I would want to find the antiderivative of this function, e to the minus st f prime of t. I can go off to the side and figure out that antiderivative, and I would like to do integration by parts to it. What would be a smart choice is to let dv be f prime of t, because that way v would be the antiderivative, which is just f. Meanwhile, I'm going to make u the other part, which makes du whatever it is, which is this. And so I do integration by parts. I get uv minus the integral of v du. So here's uv, and here's the integral of v du. Of course, this is just another way of writing this antiderivative. To do the Laplace transform, I'm supposed to do that integral from 0 to infinity. In other words, I would take this from 0 to infinity. So what happens is, when I take this part from 0 to infinity, that's like I do it from 0 to b, and I do the limit as b goes to infinity. Meanwhile, when I do this part, whoops, I forgot to write the limits here. I do this also from 0 to infinity. And what do I get? Well, this one, because f has exponential order, if s is big enough, this integral converges. In other words, when I do the limit as b goes to infinity, this part goes to 0. When I plug in b and do the limit as b goes to infinity. What's left over is what I get when I plug in 0. And when I plug in 0 here, I get e to the 0 times f of 0, which is this. And it has a negative sign because you subtract the bottom number. Right? So this is this, and this is just this, because this integral, and by the way, this s came outside, this s was here, and I canceled the negative sign. I pulled the s out, and that's how we got here. And this integral that I just underlined is the Laplace transform of f. So this is s times the Laplace transform of f. So that's why we have this rule. Okay, now let's use that to solve a differential equation. We're going to start real small here. Y prime equals 2y and y of 0 equals 1. This is something that we could have done on the first day. This is a separable differential equation, but we're going to use this as a warm-up to solve a differential equation using a Laplace transform. So I am about to do L of both sides, the Laplace transform of both sides. Let me, and I'm going to use like lowercase y of t as the original function, and I'll use capital Y, and capital Y is really a function of s, for the Laplace transform of little y. So here I go. I'm about to do the Laplace transform of both sides. In fact, I'm not going to do a whole lot in this step. I'm really just writing what I'm doing. I literally just did L of both sides, and I'm emphasizing that these are functions of t, so y prime of t and y of t. On the left, I get s times the Laplace transform of y minus y of 0. S times the Laplace transform of y minus y of 0. That's what I get on the left. On the right, 2 is just a constant multiple. The Laplace transform of little y is big Y. And maybe I'm writing too much for this. Normally we just write y prime. I don't write y prime of t. Normally I would also write capital Y. I wouldn't really write capital Y of s. The only reason why I'm writing this is to emphasize what the variable is. Like, these are functions of t, these are functions of s. When you get more comfortable with this, you can just write little y and capital Y, and it's understood that the lowercase letters are functions of t, the capital letters are functions of s, because they're Laplace transforms. Anyway, we get this, and this is now, it's like no longer a calculus problem. This is an algebra problem. I can just solve for capital Y of s. So I would move this over, and I'm going to move the 1 over. And I'm getting all the y's on the left, and I'm going to factor y out of that. And on the right, all I have is this 1. And then I get capital Y of s is 1 over s minus 2. So this is the Laplace transform of my function y. Of course, the real problem was to find the original function, little y, so I'm not done. However, this is what we have inverse Laplace transforms for. You hear the pages flipping because I was flipping to this page. So I know that the Laplace transform of my function is 1 over s minus 2. I would like to find the original function. So I see this entry, 1 over s minus a, and it looks like my a would be 2. And so the inverse Laplace transform of that would be e to the at. So my little y, which would be the inverse Laplace transform of 1 over s minus 2, would be e to the at, so e to the 2t. And that was the answer we were expecting, that is the solution to this differential equation. We could have figured it out, you know, the separable differential equation way, and we would have gotten the same answer. Yeah, so then I think I have time to do another example. It's going to be almost the same, actually. it's just y prime is 2y plus t. The last one, y prime, was just 2y. So let's think about this one. I would do the same. I mean, fundamentally, my first step is the same. I do the Laplace transform of both sides. On the left, everything works out the same because, I mean, actually my initial condition is even the same, y of 0 equals 1. So when I do the Laplace transform of y prime, I get s times the Laplace transform of y. And like I said, this time I'm not going to bother writing y of s. It's understood that y is a function of s. So it's s times the Laplace transform of y minus y of 0, which is 1. And that's the same as what we got last time. The Laplace transform on the right is going to be different. This is just 2 times the Laplace transform of y. This, I have to remember what is the Laplace transform of t. Luckily, I have my table. Laplace transform of t is 1 over s squared. So I've got that. So once again, this is now like a little algebra problem. I'm going to get all my y's on the left, and everything that doesn't have a y on it I'm going to get on the right. So, and on the left I'm going to factor out the y. So on the left I would have s times y minus 2 times y. And on the right I would have 1 plus s squared. 1 plus 1 over s squared, which if I get a common denominator is s squared plus 1 over s squared. So y is s squared plus 1 over s squared s minus 2. Right? And now we're at this point where this is the Laplace transform of my answer. All I need to do is the inverse Laplace transform of this. However, this is not exactly something that I see on my list, right? This complicated looking thing, s squared plus 1 over s squared times s minus 2. I don't really see anything quite like that on my list. So how am I going to do the inverse Laplace transform of it? Well, partly the answer is that I'm going to cheat, but I'm not fundamentally cheating. I just want to make the work go a little bit faster. So what I did in Maple is I took that and I converted it into partial fractions. This is the command to do that, by the way. This is a very handy thing to know how to do with Maple. And Maple tells me this: 5 over 4s minus 2 minus 1 over 2s squared minus 1 over 4s. So but like I said, I don't consider this fundamentally cheating. This is something that we could have done by hand. We all theoretically know how to do this by hand. I just didn't want to do it by hand right now. I'm copying down what Maple told me. Like this. So this and this are the same thing, and we all know how to do partial fractions. It's just maybe slightly painful, but we know how to do this work. Now I can do the inverse Laplace transform of this. So the original function y is going to be, okay, first of all I have the inverse Laplace transform of this, which is going to be 5/4, because the constant comes right down. And then 1 over s minus 2, that one was here, that's e to the 2t. right, minus 1/2 times the what's the inverse Laplace transform of 1 over s squared? It's t. Minus 1/4. Now, what's the inverse Laplace transform of 1 over s? Well, that's just 1. So I can write times 1 if you like, but I'll just not. So that's it. That's the answer. So I'll be back next time. We're not quite done with 10.2 yet because we can also do higher order differential equations, like with y double prime and stuff. But to do that, you will have to know how to do, like, what's the Laplace transform of y double prime. And that's not that much harder, like the formula's in the book, and I'll tell you what it is too. But anyway, we'll get there when we get there. So that's it for now.